Let's get tape machines. This is sort of fun. These reels of tape that you see on the machine here, they used to cost about $200 a reel, and at 30 inches per second hold 15 minutes of recorded material. And the one you're looking at right now, this is my tape machine, 24 tracks, and you got 15 minutes of recording. So it wasn't terribly efficient compared to digital recording. We'll get to the digital part, and then at the end we'll compare the two a little bit. This would be the tape path. There's a supply reel and a take-up reel. So the supply obviously supplies the tape. Number one here in the picture is a tension arm that keeps tension on the tape so that it flows smoothly across the heads. And it's really important, these tension arms, because the way that they used to work is the position of these arms would tell the reels how much tension to either supply, how much tape to supply, or how much tape to pull back and take up. So these machines had to run at even speeds from beginning of the reel to the end of the reel. And the one real problem is that the tape is really heavy. It's basically a mylar backing with iron oxide on it. So this reel of 2-inch tape is like a piece of iron pretty much. It's pretty heavy. So when there's more tape on the supply reel versus the take-up reel, there's more torque needed to pull the tape across the heads. When there's more on the take-up reel than the supply reel, the tensions all and the torque of each reel has to adjust. A very complex kind of situation, and actually an engineering marvel when it works right. When it doesn't work right, it's a real headache, because you're there with a screwdriver trying to adjust things and make it work right, and things are speeding up and slowing down and not sounding right. Let me continue. Number two is an idle roller to help the tape proceed through past the heads. Number 4, 6, and 7 are the heads, and they appear as the tape passes from the supply reel to the take-up reel as the erase, the overdub head or the sync head, because things are synchronized on that head. Things play back and record from that head. And number 7 is only a playback head. And they used to do these 3 heads because obviously if you're recording over something that's been recorded, you have to erase it before you can record on it. And number 7 is the playback head, which had better electronics associated with it to be just used for playback and mixdown. The head number 6, or the middle head, the record head, or sync head, there's a couple names. It's called a record head, it's called a sync head, and the record head actually records what's being put on the tape new, and it also plays back the tracks that have been previously recorded so you can hear them. And you see that they're in the same physical location as the tape moves by. So you're hearing everything in sync with what you're recording if you're working off the head that's labeled 6. 5 are the tape lifters. So when the tape is rewinding or fast forwarding, these lifters come out to keep the tape off the heads, because all of the friction on the heads of the tape can wear down the heads and wear out the heads. And the heads are extremely important. The heads are actually electromagnetic transducers, different than a microphone, but they work in a similar fashion where they either spit out magnetic flux or read magnetic flux and change it into electrical energy. If they're reading, they change magnetic flux into electrical energy. If they're recording, they take electric energy, change it to magnetic energy, and spit it out so that the tape, as it's passing, can capture it and be magnetized in certain areas. Number 8 is the capstan, and number 9 is the pinch roller. So when you're playing, the pinch roller and the capstan snap together, and the capstan is what sets the speed so that it's going to be a precise speed of 30 inches per second or 15 inches per second or whatever speed you choose. And the pinch roller basically keeps this all intact. The way it really works is that number 8 is the capstan, and this is a top view. That's actually a cylindrical piece of metal that snaps across the tape and is running at a constant speed. And the supply and take-up reel have to adjust how much torque they have to keep the tape from either going too fast through the heads or too slow through the heads. It's a pretty intricate mechanical device. And this took a lot of years of engineering skill to be able to pull this off. So, mechanically, primary function is to shuttle tape and keep it running at a constant speed. Electrically, operation is to modulate the input signal with the bias signal. I'll explain what a bias signal is in a second. With a bias signal, audio function is to adjust frequency of the signal to be recorded so the tape records almost linearly with the signal coming in. So you're trying to keep all of the frequency levels even. You want a flat frequency response in and out of your tape machine. So it is true to what you put in, comes out the same way. It's really just a storage device. And you're using transducers to change domains of the energy so it can be stored in an accurate way and then played back. Magnetic, the tape heads convert electrical to magnetic and magnetic to electrical signals for record and playback. And the tape itself stores the magnetic impulses. So that's the basic overview of how it works. The tape machine, let's talk about the machine bias, as I said that I would talk about. So the bias, this is a pretty complicated process as to how it really works. So the bias signal is a high frequency signal that's very loud, and it becomes the carrier signal for the audio to be recorded. And I'll explain why it's necessary. So you've got a frequency of 20,000 hertz, and its level is being modulated by the audio that you're trying to capture. The reason that you need a bias signal, it's kind of complicated, but it's a very good reason. Let me get through the card, and then I'll explain in more detail why you need a bias signal in the first place. The audio signal modulates the bias signal when the bias signal gets filtered out at the end of the process, so you're only left with the audio signal. Let's start at the beginning. So a signal comes into an analog tape machine from a microphone. It's an electrical signal that represents the audio acoustical sound that was being recorded. It goes into the tape machine. It gets combined with a high frequency, very loud signal of a bias frequency, and it modulates the bias frequencies. Then it gets recorded onto analog tape, which is magnetic. And then on the playback side, the tape goes by the playback head, reads the magnetic fluctuations, and then the electrical portion of the machine then filters out the bias signal, and all you're left with is your original analog signal. And you might say, well, why is that important? It's very important because magnetic tape is not a linear medium. Basically, and I'll get into a little bit of how tape works and what it's made of, magnetic tape is a very crucial part to the whole analog recording process. Scotch, 3M, there were a number of companies that Ampex made their own magnetic tapes, and they all had their own formulas as to how they would make the tape, so it would operate a little differently and sound a little different. But in general, if you take a piece of magnetic tape and you put an input signal in, you got to get a certain amount of level on it before it starts operating in a more linear fashion. So if I was to try to record a low-level signal onto a piece of analog tape, it wouldn't have enough energy magnetically to actually work with the tape. So you almost have to put the magnetic tape into a position where it's kind of running and ready to go. Here's a great example to explain it a little more clearly. So if you're in your car and you're driving on the freeway, to speed up is not so hard. The car's already in motion. But if you're at a dead stop and you need to speed up, it takes more energy to get going. And that would be what the bias signal basically does, is it puts the magnetic tape into a position where it's already in action and ready to go. And then you can add on top of that your little audio signal. And so it's easy to capture those little fluctuations. And then at the end of the day, when you're trying to listen back to those little fluctuations, the machine itself filters out the signal that actually put the tape in motion in the first place. I'm tempted to get into the process of analog tape because that would make it much more clear, but I'll get to that in a second. So analog tracks. On analog tape, each track is a discrete stripe on the tape itself. The tape is covered with a coating of magnetic oxide, which is magnetized by an audio signal running into the record head. Right? So magnetic flux comes out of the record head. And the tape machine that you saw in the beginning of this slide, when you saw the tape machine, that was a 24-channel tape machine, a 24-track tape machine. This magnetism can be read and played back by the playback heads and turn back into electrical signal. Let's look at some of the common formats of tape on a more practical level. You've got a 30 inches per, these are common speeds that we used to record at. 30 inches per second, 15 inches per second, 7.5, 3 3/4, and 1 7/8. The slower speeds, the 1 7/8, was what a cassette did in terms of its speed. Not really a pro speed. As you get faster and faster, the frequency response gets better and better of the tape. So we used to record at 30 inches per second or 15 inches per second. The tape widths that we used to use is 2 inch, and that is 24 tracks or 16 tracks. Before we went to digital, everyone was pretty much using 30 inches per second and 24 track tape machines. But 15 inches we used to use occasionally to track drums on a 16-track 2-inch machine that was running at 15 inches per second. Because it was running slower, it didn't have quite as much transparency on the top end, but it made the drums sound a little thicker. So we used to do that sometimes. We'd also send our final masters to a 2-track running at either 30 or 15 inches per second. But these are the common speeds. 3 3/4 was sort of a consumer speed. If somebody had a home stereo with a reel-to-reel tape machine, that's the speed that they'd run at. 7.5 was the bottom end of the professional speeds, even though some people that actually had really great home stereos would run at 7.5. Okay, so analog tape, this gives you a more clear understanding. So on the left here we've got analog tape, a 1/2 inch analog tape. That means the width of the tape is 1/2 inch. And it's a 2-track, so we've got a left and a right. And this is the kind of tape that we'd master a record to, or master a recording to. And then you've got all these different formats. Eventually people got into everything from 1/4 inch 8 tracks, 1/4 inch 16 tracks, 1/2 inch 16 tracks, 1/4 inch 4 tracks, 1 inch 2 tracks, which were amazing, because the more tape exposure you have per track, the more sonic quality you'd get. So the thinner the tape track, the less quality you'd get, but you get more flexibility because you have more tracks on one piece of tape. Just as a great example, you could record on any of these formats that you chose. Mostly the demo formats were 1/2 inch and 1/4 inch, 8-track, 16-track. But that doesn't mean you couldn't have made a record on those. People even tried to release off of cassettes, but cassettes' quality were so bad that you had to really take a risk if you were going to do that. And that's why when we'd make rough mixes for clients, we'd put them on cassettes, because we knew they couldn't run out of the studio and put it on a CD and start selling it. At least that's what we thought. And it's sort of like a very compressed MP3 in today's world. It doesn't sound the same as a full WAV file.